What if the key to turning Mars into a second Earth isn't hidden in some futuristic lab, but buried deep within our own planet's ancient history? Picture this: billions of years ago, Earth was a hostile world, much like Mars is today. Yet over eons, tiny microbes, minerals, and geological processes transformed it into the lush, life-filled oasis we call home. Now, scientists believe those same ancient materials, the very building blocks that shaped our world, could be the missing ingredient to terraforming Mars. It's a mind-bending idea. The rocks beneath our feet, the fossils locked in stone, even the air trapped in ancient ice might hold the blueprint for making another planet habitable. Think about the irony here. We've spent decades looking to cutting-edge technology for answers, when the solution might have been here all along, waiting in Earth's oldest layers. From rare minerals that could stabilize Martian soil to fossilized microbes that might jumpstart ecosystems, these materials are like a time capsule, a recipe book for turning barren landscapes into thriving biospheres. And the implications are staggering. If we can decode Earth's natural terraforming process, we could fast-track Mars's transformation by millions of years. This isn't just science fiction, it's a real possibility grounded in the very science that explains how our own planet came to life. But here's the most thrilling part: this isn't just about Mars. It's about humanity's next great leap. For the first time, we're not just exploring another world, we're learning how to remake it. And in doing so, we might uncover secrets about Earth's past that could reshape our future. How did life first take hold here? What invisible forces turned a toxic atmosphere into breathable air? The answers could lie in those ancient materials, and they might hold the power to rewrite our destiny among the stars. So let's dig deep, literally, into how Earth's oldest treasures could become Mars's greatest hope, and why this mission could redefine what it means to be an interplanetary species. Terraforming sounds like something straight out of a sci-fi novel, transforming a dead, frozen world into a living, breathing one, but the science behind it is very real. Right now, Mars is a harsh desert with a paper-thin atmosphere, temperatures that would freeze you solid, and no liquid water on its surface. To make it habitable, we'd need to engineer three massive changes: a thicker atmosphere to trap heat and block radiation, stable temperatures above freezing, and enough liquid water to sustain life. Most plans today involve gigantic orbital mirrors to melt ice caps, factories pumping out greenhouse gases, or even crashing asteroids to kickstart warming. These ideas are bold, but they're also energy-intensive and could take centuries. That's where Earth's ancient history comes in. Our planet didn't need futuristic machines to become habitable, it had nature's own toolkit. Billions of years ago, Earth was just as hostile as Mars, with a toxic sky and scorching temperatures. But tiny organisms, chemical reactions in rocks, and slow geological shifts transformed it into the vibrant world we know. The key takeaway: nature already solved the terraforming puzzle. We just need to study its playbook. For example, certain minerals like olivine react with carbon dioxide, locking it away and stabilizing climates. Ancient microbes produced oxygen as a waste product, turning our atmosphere breathable over time. Even ice cores trapped in glaciers hold clues about how Earth's air and temperature shifted naturally. If we can harness these processes on Mars, we might skip the brute force approach and work with the planet's own chemistry instead. Imagine seeding Martian soil with Earth's rock-eating bacteria, or using mineral reactions to thicken the atmosphere passively. These methods wouldn't just be faster, they'd be sustainable, using Mars's own resources rather than depending on endless shipments from Earth. The beauty of this approach is that it's not just theoretical. Scientists are already testing these ideas in labs and extreme environments on Earth, from volcanic vents to Antarctic deserts. By reverse engineering our planet's past, we're not just guessing how to terraform Mars, we're following a blueprint that's been proven to work. And that could shave millions of years off the timeline, bringing us closer to the day when humans can step onto a Martian surface and breathe deeply under a sky we helped create. Earth's geological history is like a massive library, with every layer of rock acting as a page detailing how our planet survived its most extreme climate swings. Take the ice ages, for instance, entire continents buried under glaciers, only to thaw and transform into lush landscapes, or the hothouse periods when temperatures soared and oceans turned acidic. Yet life persisted, thanks in part to natural materials that acted like planetary thermostats, quietly regulating the atmosphere. Hidden in ancient sediments and rock formations are clues about how these materials stabilized Earth's climate over millions of years. And now, researchers believe these same substances could be the missing piece in Mars's terraforming puzzle. One standout example is clay minerals, which have a remarkable ability to trap carbon dioxide. On Earth, certain clays formed during periods of intense volcanic activity, locking away greenhouse gases and preventing runaway warming. Similarly, carbonates like those found in limestone naturally store carbon, acting as a long-term climate buffer. If we could locate or even manufacture these materials on Mars, they might help thicken its atmosphere while keeping temperatures stable. Imagine scattering specially treated clays across the Martian surface, where they'd absorb carbon dioxide from the thin air, gradually building up a denser, more insulating blanket. It's a subtle but powerful approach, working with the planet's own chemistry rather than against it. Then there's the role of iron-rich rocks, which played a surprising part in Earth's oxygenation. Billions of years ago, rust-colored bands formed in ancient seabeds as iron reacted with the first traces of oxygen produced by microbes. This process, called the Great Oxidation Event, slowly transformed our atmosphere into something breathable. On Mars, where iron oxide gives the planet its signature red hue, similar reactions could be jump-started with the right microbial partners. By introducing engineered bacteria that mimic Earth's early oxygen producers, we might nudge Mars toward a gentler, more Earth-like state. The real breakthrough, though, lies in combining these natural processes. Instead of relying on one giant technological fix, terraforming Mars could involve a symphony of small, self-sustaining reactions, each one borrowed from Earth's playbook. Ancient ice cores tell us how shifts in greenhouse gases influenced temperatures, while fossilized soils reveal how microbes and minerals work together to build fertile ground. Even the dust in Martian storms might hold potential, acting as a catalyst for atmospheric changes if treated with the right compounds. What makes this approach so compelling is its scalability. Unlike massive engineering projects that demand constant energy input, these methods could, once started, unfold with minimal intervention. They'd work in the background, leveraging Mars's own geology and chemistry to create lasting change. And while the timeline would still stretch across generations, it'd be a far more sustainable path, one that mirrors how Earth itself became habitable. By learning from our planet's deepest archives, we're not just guessing how to remake Mars. We're following a trail of breadcrumbs left by nature, each one pointing the way toward a future where humanity doesn't just visit the red planet, but truly calls it home. Volcanic minerals might be the unsung heroes of terraforming nature's own alchemists, capable of turning barren rock into life-giving ingredients. On Earth, volcanic eruptions didn't just reshape landscapes, they literally built the air we breathe. When ancient volcanoes spewed gases like carbon dioxide and sulfur, they also released minerals like basalt, which quietly worked behind the scenes to stabilize the climate. Basalt has a remarkable talent. It reacts with carbon dioxide, locking it away in solid carbonate forms. This process, called mineral carbonation, is like Earth's original carbon capture technology, operating on a planetary scale for billions of years. And here's the kicker: Mars is covered in vast volcanic plains, remnants of its own fiery past. Those dark, rocky expanses, they're likely packed with minerals just waiting to be activated. Imagine harnessing this natural chemistry on Mars. Instead of building massive machines to scrub carbon dioxide from the air, we could deploy crushed basalt across the surface, where it would react with the thin Martian atmosphere, pulling CO2 out of the sky and converting it into stable minerals. Over time, this wouldn't just reduce greenhouse gases, it could also release oxygen as a byproduct, edging Mars closer to a breathable environment. But the benefits don't stop there. These reactions would also produce secondary minerals like clays, which are fantastic at retaining water and nutrients. In other words, the same process that thickens the atmosphere could simultaneously transform Martian soil into something fertile, creating a foundation for future agriculture. Scientists are already testing this idea in labs, mimicking Martian conditions to see how quickly these reactions unfold. Early results are promising. Under the right conditions, basalt can lock away carbon dioxide within months, not millennia. And because Mars's low gravity and cold temperatures slow down erosion, the minerals there might remain reactive for far longer than their earthly counterparts. That means a single application of processed volcanic rock could keep working for centuries, a self-sustaining terraforming agent with no moving parts. But why stop at basalt? Other volcanic minerals like olivine are even more efficient at absorbing CO2. On Earth, olivine weathers quickly in water, making it a potential tool for accelerating atmospheric change if we can introduce it to Mars's ice-rich regions. And then there's pumice, a lightweight, porous rock that could serve as a habitat for microbes engineered to thrive in Martian conditions. These tiny organisms, paired with the right minerals, might form the backbone of a new biosphere, kickstarting the same kind of slow, steady transformation that once turned Earth from a toxic wasteland into a living world. The beauty of this approach lies in its simplicity. Unlike grandiose plans that rely on constant human intervention, volcanic minerals offer a way to work with Mars's natural systems, not against them. By studying how these materials shaped Earth's past, we're uncovering a playbook for Mars's future, one where the planet's own geology does much of the heavy lifting. It's a reminder that sometimes the most powerful technologies aren't the ones we invent, but the ones we discover, hidden in plain sight beneath our feet. Hidden within Earth's oldest rocks are tiny architects of change, fossilized microbes that transformed our planet from a lifeless wasteland into a living world. These microorganisms, some dating back over 3 billion years, thrived in conditions far harsher than anything Mars could throw at them. They survived boiling temperatures, crushing pressures, and toxic atmospheres, all while performing a quiet miracle, pulling carbon dioxide from the air and releasing oxygen as waste. Over eons, their collective breath built the atmosphere we depend on today. Now, scientists are asking a revolutionary question: could these ancient microbes, or their genetic blueprints, become the ultimate terraforming tools for Mars? The genius of these organisms lies in their simplicity. Cyanobacteria, for example, were among Earth's first photosynthetic pioneers, turning sunlight into energy while spitting out oxygen as a byproduct. Their modern descendants still exist, thriving in places like Yellowstone's scalding hot springs or Antarctica's frozen deserts, environments that mirror Mars's extremes. By studying their fossilized ancestors, researchers are reverse engineering the genetic tricks that made them so resilient. The goal, to design engineered strains capable of surviving and thriving on the red planet. Picture seeding Martian soil with these microscopic powerhouses. As they multiply, they'd not only produce oxygen but also organic compounds, slowly enriching the barren ground with the building blocks of life. But here's where it gets even more fascinating. Some of these ancient microbes didn't just tolerate harsh conditions, they actively transformed them. Certain species interacted with minerals to stabilize soil, while others produced sticky biofilms that trapped water and nutrients. On Mars, similar organisms could kickstart a cascade of changes. Imagine microbes engineered to extract water from permafrost, or to break down toxic perchlorates in the soil into harmless salts. Unlike heavy machinery or industrial processes, these tiny workers would operate silently, endlessly, and with minimal energy input. They'd be nature's own terraforming crew, operating on a molecular scale. The beauty of this approach is that it's not just theoretical. Labs around the world are already testing extremophiles in simulated Martian conditions, from vacuum chambers to radiation exposure experiments. Some teams are even resurrecting ancient genes, splicing them into modern bacteria to create hybrid strains with prehistoric toughness. Early results suggest these Frankenstein microbes could survive and function in Mars's thin atmosphere and freezing temperatures. And because they'd reproduce autonomously, their impact would grow exponentially over time. A single rover could deposit a small vial of these organisms in a strategic location, and within decades, their descendants might spread across the planet, silently prepping it for human arrival. Of course, bioterraforming isn't without risks. Introducing foreign organisms to Mars raises ethical questions about planetary protection and unintended consequences. What if these microbes mutate or disrupt potential native life? Scientists are tackling these concerns head-on, designing fail-safes like suicide genes that would deactivate the microbes if they stray beyond designated zones. Others propose starting with sealed biodomes where the process can be monitored before unleashing it planet-wide. Yet the potential rewards are staggering. If successful, this method could shave centuries off Mars's transformation timeline. Instead of waiting for giant factories to pump out oxygen, we'd let biology do what it's done best for billions of years: adapt, multiply, and reshape worlds. And in the process, we might uncover secrets about life's origins, not just on Earth but across the cosmos. These fossilized microbes are more than relics. They're living proof that the smallest organisms can achieve the grandest transformations. And on Mars, they might just get a second chance to work their magic, this time with humanity as their collaborator. Clay deposits might just be the unsung heroes of terraforming nature's original water storage system, perfected over billions of years. On Earth, certain clays like smectite have a remarkable superpower. They act like microscopic sponges, swelling to hold water and nutrients between their layers. These tiny reservoirs were critical for early life, providing stable moisture and minerals in an otherwise harsh environment. Ancient riverbeds and lake basins, now dried into rock, tell the story of how these clays helped sustain Earth's first ecosystems. And here's the exciting part: Mars has its own version of these deposits. Rovers like Curiosity have detected smectite-like clays in Gale Crater, remnants of a time when water flowed freely on the red planet. But why does this matter for terraforming? Imagine Martian soil as a parched desert, where water either evaporates instantly or sinks deep underground. Without a way to retain moisture, agriculture, and by extension, human survival would be nearly impossible. That's where Earth's clay know-how comes in. By studying how ancient clays locked in water and nutrients here, we could engineer Mars's native clays to do the same. Scientists are already experimenting with clay activation, a process where minerals are treated to enhance their water-holding capacity. Mix these supercharged clays with Martian regolith, and suddenly you've got soil that doesn't just repel life but invites it. The implications go beyond just planting crops. These modified clays could also trap atmospheric humidity, pulling trace water vapor from Mars's thin air and concentrating it in the soil. Over time, this could create self-sustaining oases, patches of land where water cycles naturally, reducing the need for constant irrigation. And because clays are excellent at binding toxins, they could neutralize harmful compounds like perchlorates, which currently make Martian soil poisonous to humans. What's truly groundbreaking is how scalable this solution could be. Unlike massive infrastructure projects, clay enhancement wouldn't require hauling heavy equipment across space. A single rover could disperse treated clay particles across strategic sites where they'd work passively, requiring no additional energy. Over decades, these patches could expand, merging into fertile zones large enough to support entire colonies. The beauty of this approach lies in its simplicity. We're not inventing something new, we're borrowing a page from Earth's oldest playbook. By understanding how our planet's clays nurtured life, we're unlocking a way to do the same on Mars, turning barren ground into a cradle for humanity's future. And in the process, we might just discover that the key to living on another world has been hiding in plain sight, written in the language of minerals and time. Rare earth elements might sound like something out of a treasure hunt, but these unsung heroes of Earth's chemistry played a starring role in making our planet habitable. Phosphates, nitrates, and other trace minerals were the invisible scaffolding for life's earliest breakthroughs, helping plants grow, fueling microbial metabolism, and even shaping the structure of DNA. On Earth, these elements are woven into ancient rocks and sediments, remnants of a time when our planet was as barren as Mars is today. But here's the catch: Mars is missing them. Scans from orbiters and rovers show strikingly low levels of these critical nutrients in the Martian soil. Without them, any attempt to grow crops or sustain ecosystems would hit a wall before it even began. So how do we solve this shortage? One option is shipping these minerals from Earth, but that's like trying to fill an ocean with a teacup: expensive, inefficient, and unsustainable. The smarter play might be synthesizing them on Mars itself. Scientists are already exploring ways to extract phosphates and nitrates from Martian rock using chemical processes inspired by Earth's own geological cycles. For example, certain bacteria on Earth can break down volcanic minerals to release phosphates, a trick we might replicate with engineered microbes on Mars. Another approach involves using concentrated acids or electrochemical methods to dissolve Martian basalt, freeing trapped nutrients in a form plants could use. But these elements aren't just fertilizer, they're also cleanup crews. Martian soil is laced with perchlorates, toxic chemicals that wreak havoc on human health and plant growth. Remarkably, some Earth minerals, like iron phosphates, can catalyze reactions that break perchlorates into harmless chloride and oxygen. Deploying these minerals across contaminated zones could detoxify the soil passively, without heavy machinery or constant human intervention. Picture a rover scattering phosphate-rich dust over future farmland, where it would work like a slow-release antidote, neutralizing poisons while simultaneously enriching the ground. The real game-changer, though, is scale. Unlike massive infrastructure projects, these solutions could start small and grow organically. A single processing unit the size of a refrigerator might produce enough nitrates to kickstart a greenhouse, with excess nutrients trickling into the surrounding soil over time. And because many rare earth elements act as catalysts, speeding up reactions without being consumed, they'd keep working long after their initial deployment. What's fascinating is how this mirrors Earth's own history. Billions of years ago, volcanic eruptions and asteroid impacts delivered these rare elements to our planet's surface, where they became the foundation for life's chemical machinery. Now, we're learning to shortcut that process, using science to compress eons of planetary evolution into decades. It's a reminder that terraforming isn't just about brute force, it's about working with the universe's hidden recipes, tweaking them to fit a new world. And in doing so, we might uncover secrets about our own planet's past, like why certain minerals became so pivotal to life in the first place. The answer could lie in the quiet power of these rare earth elements, the tiny keys that might one day unlock Mars's future. Banded iron formations are like Earth's ancient ledger entries, recording the exact moment our planet took its first breath. These striking layers of rust-colored rock, found in places like Australia's Hamersley Basin, tell the story of a world-altering shift 2.5 billion years ago when microbes began exhaling oxygen as waste. That oxygen reacted with dissolved iron in the oceans, creating thick deposits that sank to the seafloor. Over millennia, these layers piled up, forming striped patterns that geologists now recognize as evidence of Earth's great oxidation event. But here's the twist: Mars is covered in iron oxide, the same material that makes up these formations. The red planet's signature red hue, that's essentially rust, proof of iron's abundance in its soil. If we could jumpstart a similar oxygen release process there, we might unlock a self-sustaining path to a breathable atmosphere. The key lies in the chemistry. On Earth, cyanobacteria were the tiny engineers behind this transformation, using sunlight to split water molecules and release oxygen. That oxygen then bonded with iron, creating iron oxide as a byproduct. But on Mars, where liquid water is scarce and the atmosphere is thin, we'd need a workaround. Scientists are exploring two potential shortcuts: leveraging Martian minerals to mimic those ancient reactions or engineering microbes to kickstart the process. For example, certain iron-rich minerals like hematite could be chemically coaxed to release oxygen when exposed to specific catalysts or even artificial sunlight. Rovers like Perseverance have already detected these minerals in Jezero crater, suggesting we wouldn't need to start from scratch. Mars has done half the work for us. Then there's the biological angle. Modern extremophiles, descendants of those early oxygen producers, thrive in Earth's harshest environments. By tweaking their genetic code, we might create strains capable of surviving Mars's radiation and cold while performing that same oxygen-releasing magic. Picture seeding iron-rich regions with these microbes, where they'd slowly but steadily convert the planet's rust into breathable air. Unlike industrial solutions that require constant energy input, these biological factories would work autonomously, multiplying and spreading with minimal human intervention. The real beauty of this approach is its scalability. Banded iron formations didn't cover Earth overnight. They accumulated over millions of years. But on Mars, where human patience meets the urgency of survival, we could accelerate the timeline by concentrating these reactions in strategic zones. Imagine domed enclaves where engineered microbes and mineral treatments work in tandem, creating pockets of thicker, oxygen-rich air. Over generations, these pockets could merge, stitching together a patchwork of habitability. And because iron is so abundant on Mars, the raw materials would never run out. This isn't just about making air, it's about rewriting a planet's evolutionary playbook. By studying Earth's banded iron formations, we're not just peering into the past, we're drafting a blueprint for Mars's future. And in that blueprint lies a profound lesson. Sometimes the most revolutionary technologies aren't inventions, but rediscoveries. The same forces that turned Earth into a living world could one day do the same for Mars, with humanity as the catalyst. Deep beneath Earth's oceans, hydrothermal vents act like natural laboratories, churning out the perfect cocktail of heat, minerals, and chemical energy that may have sparked life itself. These underwater geysers, where scorching water erupts from the seafloor, are more than just geological curiosities. They're time capsules preserving the conditions of early Earth. What's astonishing is that Mars once had its own version of these vents. Orbital scans reveal ancient volcanic regions and dried-up channels that hint at long-lost hydrothermal activity. If life ever flickered into existence on the red planet, these vents might have been its cradle, and now they could hold the key to reigniting habitability there. The magic of hydrothermal vents lies in their simplicity. On Earth, they host thriving ecosystems in complete darkness, fueled not by sunlight but by chemosynthesis, a process where microbes convert minerals like hydrogen sulfide into energy. These extremophiles form the base of a food web that supports everything from giant tube worms to ghostly white crabs. Mars's extinct vents wouldn't need liquid water to reactivate. Even buried ice, warmed by residual geothermal heat, could create briny pockets where similar microbes might thrive. Scientists are already testing this idea in labs, simulating Martian conditions to see if Earth's vent-dwelling organisms could survive there. The results: some microbes not only endure but actively break down Martian rock, releasing nutrients in the process. But the real potential goes beyond just microbes. Hydrothermal systems are natural chemical factories. On Earth, they produce minerals like sulfides and carbonates that stabilize environments and trap essential elements. On Mars, these same minerals could be mined by robots or even harvested by future colonists to fortify soil or produce building materials. Imagine tapping into a dormant vent, using its heat to melt subsurface ice into liquid water, while the mineral-rich runoff fertilizes underground greenhouses. It's a closed-loop system requiring little external input, a stark contrast to energy-intensive surface terraforming. The most exciting part: we might not need to wait for humans to arrive. Autonomous drones could scout Mars's most promising vent sites, deploying hardy microbes or mineral catalysts to jumpstart these processes decades before the first boots touch ground. Over time, these pockets of activity could expand, creating interconnected habitable zones beneath the surface, a hidden network of life supporting oases. This isn't just speculation, it's a strategy rooted in Earth's deepest history. By studying how vents nurtured life here, we're decoding a universal playbook for turning barren worlds into living ones. And if Mars's ancient vents are as similar to Earth's as we suspect, they might not be relics of a dead past but the foundation of a living future. Permafrost isn't just frozen ground, it's a time capsule, locking away secrets from Earth's distant past in a deep freeze. Across the Arctic, scientists have discovered ancient plants, bacteria, and even viruses preserved perfectly for tens of thousands of years, waiting patiently in the ice. But here's the mind-blowing part: Mars has its own version of this frozen archive. The red planet's poles and subsurface layers are packed with ice and permafrost, possibly holding organic remnants from a time when Mars was warmer and wetter. If we could tap into these reserves, we might not just find water for future colonies, we could uncover the building blocks for an entirely new biosphere. Think of Mars's permafrost as a treasure chest buried just beneath the surface. On Earth, when permafrost thaws, it releases trapped water and nutrients, creating sudden bursts of life in otherwise barren landscapes. In Siberia, for example, melting ice has revived mosses that were frozen for over 40,000 years, still capable of sprouting anew. Now, imagine replicating this process on Mars. By strategically heating small patches of permafrost, either with solar mirrors or underground thermal probes, we could create pockets of liquid water enriched with ancient organic compounds. These oases wouldn't just sustain human settlers, they could become laboratories for studying how life might have once survived there. But the real game changer lies in the microbes. Earth's permafrost is teeming with extremophiles organisms that thrive in freezing, oxygen-starved conditions. Some of these microbes can metabolize minerals trapped in ice, slowly breaking them down into usable nutrients. If Mars's permafrost harbors similar organisms, or even their fossilized remains, we could learn how to engineer bacteria tailored to the planet's harsh environment. Picture seeding thawed zones with microbes designed to extract water from ice or convert Martian minerals into fertilizer. Over time, these tiny workers could transform sterile ground into fertile soil, kickstarting a self-sustaining cycle of growth. The implications go beyond mere survival. Permafrost is also a record keeper. On Earth, layers of ice contain air bubbles from ancient atmospheres, letting us piece together how our climate changed over millennia. Mars's ice caps might hold similar clues, traces of gases that could reveal how the planet lost its water or whether its air was ever breathable. By drilling into these frozen layers, we wouldn't just be mining resources, we'd be reading the Red Planet's autobiography, page by icy page. What makes this approach so revolutionary is its elegance. Instead of fighting Mars's harshness, we'd be working with it, using the planet's own frozen reserves to fuel its transformation. And in the process, we might stumble upon something even more profound, evidence that life isn't just a fluke of Earth, but a cosmic inevitability waiting for the right conditions to awaken. The secrets locked in Mars's permafrost could rewrite our understanding of life's resilience, proving that even in the deepest freeze, the spark of habitability never truly dies. Carbon sequestration isn't some futuristic technology, it's Earth's oldest climate hack, quietly running in the background for billions of years. Picture this: rain falls on volcanic rock, slowly dissolving minerals like olivine and serpentine. As these rocks weather, they chemically react with carbon dioxide, pulling it from the air and locking it away as solid carbonate. It's nature's carbon capture system, operating at a glacial pace but with planet-scale impact. Over millions of years, this process helped stabilize Earth's atmosphere, preventing runaway greenhouse effects that could have turned our planet into another Venus. Now, scientists are asking, could we turbocharge this same chemistry on Mars, using the Red Planet's own geology to engineer a breathable future? The challenge is stark. Mars's atmosphere is 96% carbon dioxide, but it's so thin that it can't trap enough heat to sustain liquid water, let alone human life. The irony: there's too much CO2 for humans to breathe, yet not enough to warm the planet effectively. That's where Earth's rock-based carbon tricks come in. By scattering reactive minerals like crushed olivine across Mars's surface, we could trigger artificial carbonation. These minerals would bind with atmospheric CO2, forming stable carbonates while simultaneously thickening the air. It's a two-for-one deal, reducing greenhouse gas concentrations while increasing atmospheric pressure, inching Mars closer to the Goldilocks zone where humans could survive without pressurized suits. But here's the genius part: we wouldn't be starting from scratch. Mars is already rich in the exact minerals needed for this process. Orbital surveys reveal vast deposits of basalt, a volcanic rock that's particularly good at carbon sequestration. And because Mars lacks Earth's relentless erosion and plant cover, its rocks are fresher, more chemically reactive. In lab simulations, Martian basalt has shown an impressive appetite for CO2, especially when exposed to even trace amounts of water. That means a single rover could distribute mineral dust across strategic regions, where natural windstorms would spread it further, creating a self-sustaining carbon sponge. The real breakthrough, though, lies in scaling this up. On Earth, carbonation takes centuries, but Mars offers unique advantages: frigid temperatures that prevent carbonates from breaking down, and ultraviolet radiation that could accelerate certain reactions. Scientists are even exploring bio-enhanced weathering, engineering microbes to secrete acids that speed up mineral breakdown. Imagine drones dropping pellets of mineral powder seeded with these microbes across Mars's deserts. Over decades, the combination of biology and geology could transform the atmosphere passively, with no factories or energy-intensive machines required. This isn't just theory. Iceland's Carbfix project already injects CO2 into basalt formations, where it mineralizes in under 2 years. On Mars, where basalt blankets much of the surface, the potential is staggering. By borrowing Earth's oldest climate stabilization strategy, we're not just terraforming another world, we're proving that the best solutions are often the ones nature perfected long before we arrive. And in the process, we might uncover secrets about our own planet's past, like how carbon cycles saved Earth from becoming a perpetual hothouse. The rocks beneath our feet have been climate engineers for eons. Now it's time to let them work their magic on Mars. Beneath our feet lies an ancient instruction manual, pages written not in words, but in layers of fossilized soil known as paleosols. These time-stamped snapshots capture moments when barren rock first transformed into fertile ground, recording the precise chemical handshake between minerals, water, and early life. One standout player in this transformation was glauconite, a greenish mineral that acts like nature's slow-release fertilizer. Formed over millennia in marine sediments, glauconite holds potassium, iron, and other essential nutrients in a molecular cage, gradually dispensing them as plants or microbes demand. It's Earth's original soil amendment, perfected long before humans invented agriculture. And on Mars, where the regolith lacks nearly everything plants need to thrive, this ancient mineral could hold the key to turning sterile dust into thriving farmland. The magic of glauconite lies in its patience. Unlike synthetic fertilizers that flood soil with nutrients only to leach away, this mineral weathers slowly, maintaining balance in harsh environments. On early Earth, glauconite-rich soils supported some of the first land-based ecosystems, stabilizing nutrients against erosion and extreme climate swings. Mars presents similar challenges. Its thin atmosphere offers little protection against radiation, and temperature fluctuations could strip away fragile topsoil. But glauconite's resilience against degradation makes it an ideal candidate for Martian agriculture. The question isn't just whether we can find it on Mars, it's whether we can recreate the conditions that birthed it on Earth. Here's where paleosols become our Rosetta Stone. By studying how ancient wetlands and shallow seas fostered glauconite formation, scientists are reverse engineering the recipe. The process requires 3 key ingredients: iron-rich clay, organic matter, and time, lots of time. On Mars, we might shortcut that timeline. Lab experiments show that mimicking marine conditions with electrolysis can accelerate glauconite production from basaltic dust. Pair this with engineered bacteria that secrete binding agents, and suddenly, what took nature millions of years could unfold in decades. Imagine robotic rovers scouring Martian clay deposits, processing them into glauconite-infused soil blends, and spreading them across designated farm zones. Each patch would act like a nutrient battery, charging the ground for generations of crops. But fertility isn't just about minerals, it's about structure. Paleosols reveal another secret: the intricate dance between particles and pore spaces that allows roots to breathe and water to flow. Martian regolith is notoriously fine and compacted, more like talcum powder than loamy earth. Ancient soils solved this problem with organic glues biofilms from microbes that clump particles into crumbs. Replicating this on Mars might involve seeding treated regolith with fungi or bacteria that excrete sticky polymers, building soil structure from the bottom up. Over time, these engineered ecosystems could become self-sustaining, with glauconite supplying nutrients and microbes maintaining the scaffolding. The implications stretch far beyond growing lettuce in domes. If we can bootstrap Martian soil to mimic Earth's paleosols, we're not just farming, we're terraforming. Plants grown in this enriched regolith would release oxygen, stabilize dust storms, and even help regulate temperature through transpiration. And because glauconite's nutrients are locked in mineral form, they'd resist being blown away by Mars's relentless winds. This isn't just agriculture, it's planetary-scale gardening, using Earth's oldest soil strategies to cultivate an alien world. What's most striking is the elegance of this approach. Instead of forcing Mars to conform to our expectations, we're learning to speak its geological language. Paleosols teach us that fertility isn't a stroke of luck. It's a chemical conversation between rock and life, written over eons. By decoding that conversation, we're not just preparing to grow food on Mars. We're learning how to help Mars grow into itself. Earth's extremophiles are the ultimate survivalists, thriving in places that would kill most life in seconds, boiling acid pools, crushing ocean depths, even the vacuum of space. These microscopic champions have cracked the code to living in conditions almost identical to Mars's brutal environment. Take Deinococcus radiodurans, a bacterium so tough it's nicknamed Conan the Bacterium. It can shrug off radiation doses thousands of times stronger than what would vaporize a human, repairing its shattered DNA like a biological superhero. Or consider Sulfolobus, an archaeon that bathes in sulfuric acid and scorching heat, happily metabolizing sulfur as if it were a gourmet meal. These organisms aren't just curiosities, they're living proof that life can adapt to the harshest corners of the universe. And that makes them the perfect pioneers for terraforming Mars. But how do we take these earthly survivors and put them to work on another planet? The answer lies in their genetic toolkits. Deinococcus, for example, packs its DNA into ring-shaped structures that act like shock absorbers, preventing radiation from breaking critical genetic code. Other extremophiles produce proteins that act like molecular antifreeze, keeping their cells functional in sub-zero temperatures. By splicing these adaptations into crops or soil microbes destined for Mars, we could create organisms that don't just endure the red planet's challenges, they thrive in them. Imagine wheat engineered with radiation-resistant genes, growing under Martian skies without needing shielded domes, or cyanobacteria tweaked to photosynthesize in dim sunlight, pumping out oxygen while weathering dust storms. The real breakthrough, though, isn't just copying nature, it's improving on it. Scientists are already experimenting with directed evolution, exposing extremophiles to Mars-like conditions in labs and selectively breeding the hardiest strains. Some teams are even using CRISPR to hybridize traits, creating super microbes that combine radiation resistance with the ability to break down perchlorates, the toxic chemicals lacing Martian soil. The goal, organisms that terraform autonomously, requiring no more maintenance than a dandelion pushing through a sidewalk crack. What's astonishing is how quickly this could scale. A single vial of engineered microbes dropped into the right Martian niche might multiply and spread across the planet, subtly transforming the environment generation by generation. In Antarctica, researchers have watched bacteria colonize barren rock within years, slowly weathering it into soil. On Mars, a similar process could unfold, with extremophiles mining nutrients from regolith, stabilizing dunes, and even creating thin layers of organic matter. The first whispers of topsoil on a world that's never known it. This isn't just about survival, it's about rewriting the rules of what's possible. By harnessing the ingenuity of Earth's toughest organisms, we're not just preparing to live on Mars. We're learning how to let Mars live, and in doing so, we might discover that the line between a dead planet and a living one isn't as stark as we once thought. It's just a matter of finding the right pioneers to cross it. Sedimentary layers are Earth's history books, each page a snapshot of how our planet transformed from a lifeless rock into a living world. Take the Grand Canyon. Its colorful bands reveal ancient oceans, shifting deserts, and volcanic eruptions stacked like chapters in a geologic novel. These layers don't just tell stories, they hold practical secrets. Coal seams, for instance, are the fossilized remains of lush carbon-rich swamps, while limestone deposits mark vanished seas teeming with shelled life. Now, imagine reading Mars's sedimentary record with the same precision. The red planet's Gale crater, explored by NASA's a Curiosity rover, shows striking similarities, alternating bands of sandstone and mudstone that whisper of ancient rivers and lakes. But here's the game changer. Buried within those layers could be the very materials we need to terraform Mars, hidden in plain sight. The key lies in the chemistry of sedimentation. On Earth, certain layers concentrate minerals like gypsum or hematite, formed when water interacted with specific elements. These marker beds act like signposts for geologists, pointing to regions rich in usable resources. Mars's strata likely follow the same rules. For example, sulfate-rich layers spotted by rovers hint at past evaporation events, periods when water vanished, leaving behind salts and other compounds essential for soil enrichment. By mapping these layers globally, we could create a treasure map for terraforming, targeting zones where critical minerals are most abundant. No need for blind drilling or guesswork. The planet's own history would guide us. But the real gold mine isn't just minerals, it's biosignatures. Earth's sedimentary rocks preserve microscopic evidence of early life, from fossilized microbes to organic molecules. If Mars ever hosted life, even briefly, its strata might hold similar traces. Discovering these wouldn't just rewrite astrobiology textbooks, it could offer a shortcut for terraforming. Imagine finding ancient microbes adapted to Martian conditions, organisms we could revive or genetically tweak to jumpstart ecosystems. Even fossilized remains could reveal how life interacted with the planet's chemistry, providing blueprints for engineering modern solutions. The beauty of this approach is its efficiency. Instead of blanketing Mars with Earth materials, we'd surgically extract what's already there, leveraging billions of years of natural sorting. Wind and water did the heavy lifting long ago, depositing resources in predictable patterns. By reading these layers like a manual, we could prioritize sites where terraforming ingredients are concentrated clays for water retention in one region, carbonates for atmospheric buffering in another. It's a strategy rooted in planetary patience, working with Mars's geologic legacy rather than against it, and the implications stretch beyond resource hunting. Sedimentary layers are climate archives. On Earth, alternating bands of dark and light shale correspond to ice ages and warming periods, etched by subtle changes in ocean chemistry. Mars's strata might hold similar clues, revealing how the planet lost its water or why its atmosphere thinned. Decode those patterns, and we're not just mining, we're learning how to rebalance an entire world. The rocks beneath our feet have already written the playbook for planetary change. Now it's our turn to read it. Meteorites are more than space debris, they're cosmic messengers, carrying minerals forged in the fires of ancient asteroids and planets. And here's the mind-bending part. Some of these extraterrestrial rocks contain minerals identical to those found on Mars, like magnetite, a naturally magnetic compound. It's as if the universe left us a trail of breadcrumbs linking Earth and Mars through shared geology. These overlaps aren't just curiosities, they're clues to universal processes that shape rocky worlds. If we can decode how these minerals behave in different environments, we might unlock game-changing tools for terraforming, like using magnetic minerals to create natural radiation shields on Mars. Take magnetite, for example. On Earth, it forms in volcanic eruptions and hydrothermal vents, but it's also been found in Martian meteorites like LH84001, which famously sparked debates about potential fossilized life. What makes magnetite so fascinating is its dual role. It's not just a mineral, it's a tiny compass. When scattered in soil or embedded in rock, its magnetic properties can deflect charged particles, exactly the kind of harmful solar radiation that bombards Mars's surface. Imagine sprinkling magnetite-rich dust over habitats or mixing it into construction materials, creating passive shielding that requires no energy or maintenance. It's a concept borrowed from nature itself. Some bacteria even use magnetite crystals to navigate Earth's magnetic field, but the connections go deeper. Certain meteorites also contain jarosite, a sulfate mineral that forms in acidic water. On Mars, jarosite dots the dry lake beds of Meridiani Planum, proof that liquid water once flowed there. By studying how these minerals interact with Earth's atmosphere and moisture, we're essentially running a dress rehearsal for Mars. For instance, jarosite breaks down over time, releasing sulfur and iron, key nutrients for potential crops. If we can replicate that process in controlled Martian greenhouses, we might turn toxic soil into fertile ground using materials the planet already has. The real magic lies in the universality of these minerals. They're not limited to Earth or Mars. They're found in asteroids, moons, and even distant exoplanets. That means the lessons we learn from meteorites could apply far beyond our solar system. Picture a future where explorers land on a new world and immediately scan for familiar minerals, using their properties to build shelters, purify water, or generate breathable air. It's cosmic chemistry at its most practical, a toolkit written in the language of rocks, waiting to be read. What's thrilling is how humble these minerals seem until you grasp their potential. Magnetite isn't just a rusty curiosity. It could be the key to surviving on Mars. Jarosite isn't merely a relic of dead lakes. It might help feed future colonies. These meteorite messengers remind us that the universe operates on repeatable patterns, and by understanding them, we're not just studying other worlds, we're learning how to rebuild them. Biogenic minerals are nature's collaboration between geology and life, proof that rocks and biology don't just coexist, they co-create. Take pyrite, often called fool's gold. On Earth, its shimmering crystals frequently form with the help of sulfur-loving bacteria that thrive in oxygen-starved environments like deep-sea vents. These microbes rearrange atoms as they metabolize, leaving behind mineral signatures unmistakably shaped by life. Now, imagine finding pyrite on Mars with the same telltale structures. It wouldn't just hint at ancient organisms, it could reveal how they interacted with the planet's chemistry, a roadmap for replicating those processes today. But the real power of biogenic minerals isn't just in their past, it's in their potential. Apatite is the perfect example. This unassuming phosphate mineral is a vault for phosphorus, the backbone of DNA and a linchpin for agriculture. On Earth, apatite often forms in the presence of microorganisms, concentrating phosphorus in deposits that eventually fertilize soil. If Mars harbors similar formations, they could be mined not just for science but for survival. Picture crushing Martian apatite into dust, then seeding it with engineered bacteria designed to unlock its phosphorus slowly, creating self-sustaining fertilizer factories on a planet with no natural nutrient cycles. It's a closed-loop system where the very minerals shaped by ancient life could nurture new life in the future. The brilliance of this approach lies in its efficiency. Unlike hauling tons of fertilizer from Earth, we'd be tapping into Mars's own geologic pantry, and the possibilities don't stop at apatite. Consider stromatolites, those layered mounds built by cyanobacteria over millennia. Fossilized stromatolites on Mars could teach us how to grow artificial versions, mineral scaffolds infused with oxygen producing microbes. These living rocks would serve dual purposes, terraforming the atmosphere while stabilizing loose regolith against Mars's relentless dust storms. Here's where it gets even more fascinating. Biogenic minerals often have quirky properties honed by their biological origins. Some pyrite, for instance, conducts electricity unusually well due to organic residues trapped in its structure. On Mars, such traits could be harnessed for unconventional tech, like mineral-based circuits printed directly onto rock surfaces, eliminating the need for rare earth metals. Or take magnetotactic bacteria, which align magnetite crystals into microscopic compass needles. Tweaked for Martian conditions, they might help orient solar panels or guide autonomous rovers without GPS. The irony is poetic. For decades, we've searched for signs of past life on Mars as a way to answer existential questions. But those very signs, if we find them, could become practical tools for humanity's future there. Biogenic minerals blur the line between discovery and utility, turning fossils into foundations. They remind us that life doesn't just adapt to environments, it engineers them, leaving behind blueprints in stone. And on Mars, those blueprints might be the key to writing a new chapter, one where life, once a passenger, becomes the architect. Silica might seem like ordinary sand, but in the right conditions, it becomes one of nature's most remarkable preservatives. On Earth, ancient deposits like chert, a hardened form of silica, have locked away microscopic fossils for billions of years, capturing snapshots of some of the earliest life forms. These rocks don't just fossilize cells, they trap entire ecosystems in stunning detail, from the coiled strands of prehistoric bacteria to the delicate structures of microbial mats. What makes silica so special is its ability to encase organisms almost like amber, sealing them in a protective glassy matrix that resists decay and radiation. And here's the exciting part. Mars has its own version of these silica-rich formations. NASA's Spirit rover stumbled upon nearly pure silica deposits in Gusev crater, a discovery that sent shockwaves through the scientific community. If Earth's chert is any guide, these Martian outcrops could be hiding secrets far more valuable than water. They might hold clues to whether life ever gained a foothold on the red planet. But silica's potential goes beyond just preserving fossils. On Earth, certain types of hydrated silica act like sponges, absorbing and trapping water molecules within their crystalline structures. These water-rich silicates could be literal oases on Mars, locking away moisture in the dry Martian soil. Future colonists might one day mine these deposits, using simple heating techniques to extract drinkable water, or even split it into hydrogen and oxygen for fuel. And because silica is an excellent radiation shield blocking harmful cosmic rays far better than metals or regolith, these same deposits could become natural bunkers for habitats. Picture tunneling into a silica-rich hillside, where the walls themselves provide protection while potentially harboring untapped water reserves. The real magic lies in how these processes mirror Earth's own history. In places like Yellowstone's hot springs or Iceland's geothermal fields, silica precipitates out of mineral-rich waters, creating terraces and crusts that teem with extremophile microbes. These environments are analogues for what might have once existed on Mars, where volcanic activity and hydrothermal vents could have fostered similar silica formations. By studying how life interacts with silica on Earth, we're essentially decoding a universal playbook for habitability. If microbial life ever existed on Mars, silica deposits would be the perfect place to look for its remnants, not just because they preserve organisms, but because they might have provided refuge during the planet's drying phase, sheltering life in microscopic pockets of moisture long after the surface became barren. What's most compelling is the duality of silica. It's not just a relic of the past, it could be a cornerstone of Mars's future. As a building material, silica-based glass or concrete would be ideal for 3D printed habitats, combining strength with radiation resistance. As a water source, it could sustain early outposts without relying on costly shipments from Earth. And as a scientific treasure trove, it might finally answer the question that's haunted us for centuries: are we alone in the universe? The same silica that recorded Earth's earliest life could one day reveal Mars's hidden story, if we know where to look. Salt flats are nature's paradox, bone-dry landscapes that somehow hold the secret to water survival. Take Chile's Atacama Desert, one of Earth's driest places, where salt crusts shimmer under relentless sun. Yet hidden beneath that cracked surface, microbes thrive in microscopic pockets of moisture, clinging to life by extracting water directly from the air. These salts, like gypsum and halite, act like sponges, absorbing trace humidity at night and releasing it during the day. It's a delicate dance of condensation and evaporation, perfected over millennia. Now, zoom out to Mars, where orbital scans reveal vast stretches of sulfate salts eerily similar to Atacama's. If life can hack survival in Earth's salt flats, could these Martian deposits be doing the same thing, locking away precious water molecules in plain sight? The implications are staggering. Instead of drilling deep for ice or hauling water from Earth, future colonists might tap into these salt reservoirs using nothing more than passive collectors. Picture lightweight mesh nets spread over Martian salt pans, designed to mimic the natural condensation process. As temperatures drop overnight, salts would pull moisture from the thin atmosphere, forming briny droplets that could be funneled into storage tanks. Early prototypes on Earth already prove the concept works. Some desert communities use salt-based traps to harvest drinking water from air with zero energy input. On Mars, where every drop counts, this low-tech solution could be revolutionary. But salts aren't just water banks, they're potential energy stores too. On Earth, certain salt flats double as giant batteries. When dissolved in water, salts like lithium sulfate can conduct electricity, making them ideal for renewable energy storage. In Chile's Salar de Atacama, lithium mining supports global battery production. Mars's sulfate-rich regions might serve a similar purpose, not for lithium but for thermal energy. Salt compounds have an incredible capacity to absorb and retain heat, releasing it slowly over time. Imagine lining greenhouse foundations with salt-infused materials, creating a thermal buffer against Mars's freezing nights. Or using molten salt reactors, already tested in Earth solar plants, to store excess energy from Martian solar arrays. What makes this approach so elegant is its simplicity. Unlike complex machinery prone to failure, salt-based systems leverage chemistry that's been reliable for billions of years, and the raw materials are already there, scattered across Mars's surface like a forgotten toolkit. By studying how Earth's salt flats function from the microbes they shelter to the energy they trap, we're not just solving Martian challenges, we're rediscovering ancient survival strategies, written in crystals and dust, waiting for us to read them. The same salts that give the Atacama its otherworldly glow might one day light up a Martian outpost, proving that sometimes the best solutions aren't invented, they are inherited. Peat bogs are Earth's silent climate warriors, swampy archives where time stands still. Layer upon layer of ancient moss and plants pile up, barely decomposing in the waterlogged, oxygen-starved environment. Over thousands of years, these soggy vaults lock away staggering amounts of carbon, keeping it from escaping into the atmosphere as greenhouse gases. But their superpower doesn't stop there. Peat acts like a giant sponge, absorbing and holding water far better than ordinary soil, preventing droughts and floods alike. It's a natural balancing act perfected over millennia. Now, picture harnessing that same dual magic on Mars, where carbon-rich air and bone-dry regolith present the ultimate terraforming challenges. The catch: Mars doesn't have sprawling wetlands or decaying plants to create peat naturally. But what if we could engineer a synthetic version? Scientists are already experimenting with biochar, a charcoal-like material made by heating organic waste in low oxygen conditions. On Earth, biochar mimics peat's carbon-trapping abilities, stabilizing soil and boosting water retention. On Mars, a similar material, crafted from processed regolith or even recycled astronaut waste, could serve as the foundation for artificial peat bogs. Imagine scattering this synthetic peat across selected regions, where it would passively pull carbon dioxide from the thin Martian air while creating pockets of moisture-rich soil. Over time, these patches could become oases, nurturing the first hardy plants engineered to survive the red planet's harsh conditions. The real breakthrough lies in scalability. Unlike massive atmospheric processors or underground ice mines, synthetic peat wouldn't demand constant energy or maintenance. Once deployed, it would work quietly in the background, leveraging Mars's own chemistry. For example, certain iron-rich minerals in Martian soil could enhance the material's carbon capture abilities, reacting with CO2 to form stable compounds. And because synthetic peat resists erosion better than loose regolith, it could anchor against Mars's relentless dust storms, preventing fertile zones from blowing away. But the most exciting possibility: these engineered bogs might do more than just store carbon and water. They could become nurseries for entirely new ecosystems. On Earth, peatlands host specialized microbes that thrive in acidic, low-oxygen environments. By introducing tailored extremophiles to Martian peat analogues, we might jumpstart a self-sustaining cycle of nutrient recycling. These microbes could break down trapped carbon into usable forms, releasing trace gases that gradually thicken the atmosphere. It's a slow process, but nature has never been in a hurry. What makes this approach so elegant is its humility. Instead of imposing Earth-like conditions on Mars, we'd be borrowing principles from our planet's most unassuming landscapes, adapting them to alien soil. Peat bogs don't dazzle with grandeur like volcanoes or forests, but their quiet efficiency is exactly what Mars needs. In the race to terraform another world, the winning strategy might not be brute force but the art of subtle, sustained mimicry, learning from Earth's oldest, wisest ecosystems. Lava tubes are nature's ready-made bunkers, twisting tunnels carved by rivers of molten rock, then left behind as empty, cathedral-like caverns when the lava drains away. On Earth, these subterranean passageways sheltered early life from extreme surface conditions, offering stable temperatures and protection from ultraviolet radiation. In places like Hawaii's Kazumura Cave or the Canary Islands' volcanic networks, scientists have found entire ecosystems thriving in these sunless corridors, from rare insects to microbial colonies that feed on mineral-rich walls. Now, orbiters circling Mars have spotted eerily similar structures, collapsed skylights, and sinuous valleys, hinting at vast lava tube networks beneath the red planet's dusty surface. These aren't just geological curiosities. They could be the ultimate cheat code for human survival on Mars. Imagine stepping into one of these Martian tubes. The temperature inside would hover around a stable -60 degrees Celsius, bitterly cold by Earth standards, but far more manageable than the surface's wild swings between freezing nights and slightly less freezing days. The thick basalt ceiling, untouched by erosion or weather, would block up to 80% of cosmic radiation, offering safer living space than any surface habitat. But here's where Earth's ancient minerals could elevate these caves from mere shelters to thriving underground oases, lining the walls with layers of olivine or gypsum. Materials known for their insulating and humidity-trapping properties could create a passive climate control system. Olivine's natural carbon sequestration might even help scrub the air, while gypsum's water-retaining crystals could regulate moisture for hydroponic farms. The real genius lies in scalability. Unlike building domes or pressurized structures from scratch, retrofitting lava tubes would require minimal construction. Robots could map and reinforce the most stable sections, then spray the walls with mineral composites inspired by Earth's most resilient cave formations. Some scientists propose 3D printing lightweight ceramic foams infused with radiation-absorbing basalt fibers, creating layered shields that mimic Earth's protective magnetosphere. Others suggest cultivating bioluminescent fungi along the ceilings, organisms already used in earthly experiments to provide low-energy lighting, transforming the tunnels into glowing, self-sustaining corridors. But the most revolutionary idea, these tubes might already hold hidden resources. On Earth, lava tubes often trap ice in their deepest recesses, where it stays frozen even in temperate climates. Mars's tubes could harbor similar deposits, offering not just water but clues to the planet's hydrological past. By combining these natural reserves with mineral-enhanced farming systems, settlers could turn these caves into vertical gardens, stacking hydroponic trays along the walls to maximize space. The result, a subterranean ark where humanity weathers the storm of Martian extremes while laying the groundwork to one day step back into the light. What's striking is how this mirrors Earth's own history. Life didn't conquer the surface overnight. It crept from protective niches like lava tubes, adapting bit by bit. By choosing the same sanctuaries on Mars, we're not just surviving, we're following a blueprint written in the bedrock of two worlds. The same forces that shaped our planet's past might now shape humanity's future, proving that sometimes the best way forward is to go underground. Roman concrete stands as a testament to ancient ingenuity. Structures like the Pantheon's dome, still intact after 2,000 years, defy modern materials that crumble in centuries. The secret volcanic ash, when mixed with lime and seawater, this humble ingredient forms a geopolymer, a stone-like material that actually grows stronger over time as it reacts with water and minerals. Now fast forward to Mars, where volcanic basalt dust blankets the surface in endless supply. What if we could borrow this ancient recipe, swapping Earth's ash for Martian regolith, to build cities that outlast anything on our own planet? The beauty of geopolymers lies in their simplicity. Unlike modern concrete, which requires energy-intensive production and emits tons of carbon dioxide, these materials harden at room temperature through chemistry, not combustion. Mix Martian soil with a binder, perhaps sulfur mined from the planet's own deposits or alkali salts extracted from dust, and you've got a paste that cures into rock. NASA already tested this in labs, crushing simulated Martian soil into powder and binding it with sulfur to create blocks twice as strong as traditional concrete. But the real breakthrough comes when we look beyond strength. Geopolymers can be 3D printed into intricate shapes, from honeycombed walls that resist quakes to arched domes that distribute weight like Roman vaults. Imagine robotic rovers scouring Mars's plains, scooping up rust-colored dust and feeding it into printers that layer entire habitats, one geopolymer stroke at a time. Here's where ancient and futuristic tech collide. While the Romans stumbled upon their formula through trial and error, we're reverse engineering it with atomic precision. Scientists now know that geopolymers gain durability from their nanostructure, a web of silicon and aluminum atoms that knit together tighter under stress. By tweaking the chemistry, we could tailor Martian geopolymers for specific tasks, radiation shielding blends infused with hydrogen-rich minerals for outer walls, or porous versions lined with silica gel to trap moisture and regulate indoor humidity. Some teams are even experimenting with living geopolymers seeded with bacteria that secrete calcium carbonate, mimicking how coral reefs grow. On Mars, such materials could self-heal cracks when exposed to the planet's trace humidity, extending their lifespan indefinitely. The implications are staggering. Instead of shipping prefab habitats at astronomical cost, we'd be building with dirt underfoot, literally turning Martian ground into cities. And because geopolymers resist corrosion and radiation better than steel or plastic, these structures could endure for millennia, long outlasting their earthly counterparts. But perhaps the most poetic twist is this: the same volcanic forces that once shaped Mars's landscape would now shape its future, not through eruptions, but through the quiet alchemy of atoms rearranging. A Pantheon's dome may have stood the test of time, but Mars's geopolymer towers could stand the test of worlds. Phosphorus is the quiet architect of life, a humble element tucked into the backbone of DNA and the energy currency of cells. Without it, nothing grows, nothing reproduces, nothing thrives. Here's the catch: Mars is desperately short on accessible phosphorus. While Earth's crust is peppered with phosphates, weathered free by rain and recycled by ecosystems, Mars's regolith locks this critical nutrient away in minerals that are stubbornly insoluble. It's a bottleneck that could derail entire terraforming efforts unless we borrow a page from Earth's ancient playbook, where life and geology teamed up to keep phosphorus in circulation. The magic of Earth's phosphorus cycle lies in its partnerships. Raindrops dissolve phosphate from rocks, rivers carry it to oceans, and microbes or plants snatch it up, weaving it into their cells. When those organisms die, decomposers break them down, returning phosphorus to the soil. It's a perfect loop, refined over billions of years. On Mars, that loop is broken. The planet's bone-dry surface and stagnant geology mean phosphorus stays trapped, like a locked pantry in a starving house. But what if we could pick that lock? One approach is brute force, mining phosphate-rich minerals like apatite, which Mars does have in trace amounts, then chemically processing them into usable fertilizer. Rovers could target ancient lake beds or volcanic regions where phosphates might concentrate, much like Earth's sedimentary deposits. Yet there's a subtler, more sustainable solution: engineering microbes to do the heavy lifting. On Earth, certain bacteria and fungi excel at liberating phosphorus from uncooperative minerals. They secrete acids or enzymes that crack open mineral cages, freeing the prized element inside. Scientists are already tweaking these organisms for Martian conditions, creating strains that can survive cold, radiation, and perchlorates while still performing their phosphorus release magic. Picture seeding treated patches of regolith with these microbes, then letting them quietly transform the soil over years. Unlike mining, which depletes resources, this method would create a self-renewing cycle, microbes pulling phosphorus from minerals, plants absorbing it, and waste or decay returning it to the ground. The real breakthrough, combining both strategies, mines could jumpstart the process, supplying enough phosphorus for initial crops, while engineered microbes gradually activate the planet's dormant reserves. Over generations, Mars's soil might evolve its own phosphorus cycle, mimicking Earth's natural rhythms. But here's the kicker: this isn't just about farming. Phosphorus is essential for every link in the chain, from soil bacteria to human bones. A closed-loop system wouldn't just feed colonists, it could sustain entire ecosystems, weaving resilience into the fabric of a fledgling biosphere. The lesson is clear: terraforming isn't just about brute force changes, it's about restarting the subtle dances that make a world alive. Phosphorus is a tiny piece of the puzzle, but without it, the picture stays incomplete. By learning from Earth's oldest partnerships, we're not just transplanting life to Mars, we're teaching it to grow there. Earth's oceans weren't always the life-sustaining blue expanses we know today. Billions of years ago, they were more like thick, salty soups with mineral concentrations that would make the Dead Sea seem mild. Yet life not only survived in these briny extremes, it thrived, evolving into organisms like halophiles, microbes that treat salt like a gourmet meal rather than a poison. These tiny survivors hold the key to one of Mars's biggest hurdles: its water. While Mars has ice and even traces of liquid brine, much of it is laced with toxic perchlorates and suffocating salinity. But what if we could borrow Earth's ancient salt lovers to turn Martian water from a hazard into a resource? Halophiles pull off some remarkable chemistry. In places like Utah's Great Salt Lake or Ethiopia's Danakil Depression, they balance internal and external salinity by producing special proteins and sugars that act like molecular sponges, soaking up excess salt to prevent cellular dehydration. Some even break down perchlorates, the same toxins plaguing Martian soil, converting them into harmless chloride and oxygen. Scientists are already experimenting with engineering these microbes for spacefaring duty, tweaking their DNA to withstand Mars's cold and radiation while supercharging their detox skills. Picture a future where rovers deploy halophile-coated filters into Martian brine pools, turning them step by step into usable water for hydroponic farms or even, one day, drinking supplies. The brilliance of this approach lies in its self-sufficiency. Unlike energy-intensive desalination plants or chemical treatments, halophiles would work passively, multiplying as they clean, requiring little more than sunlight and the very salts they're designed to neutralize. And their byproducts could be just as valuable as the purified water. Some species excrete gypsum, a mineral that stabilizes soil and retains moisture perfect for combating Mars's dust-dry regolith. Others release trace gases like nitrous oxide, which, while not breathable, could contribute to thickening the atmosphere over centuries. But the real lesson comes from Earth's own history. The transition from hypersaline oceans to today's balanced seas wasn't instantaneous. It was a slow dance between geology and biology, with microbes acting as invisible architects. Mars wouldn't need to replicate Earth's exact timeline. We could accelerate the process by concentrating halophiles in strategic reservoirs, creating pockets of habitability that gradually merge. It's a reminder that sometimes the most advanced solutions aren't about overpowering nature, but partnering with it. The same organisms that once conquered Earth's saltiest waters might now pioneer a way to make Mars's water not just survivable, but sustainable. Beneath the cracked surface of Earth's driest deserts lies a hidden world of resilient biological soil crusts, intricate living tapestries woven from cyanobacteria, lichens, and mosses. These unassuming communities are Earth's original terraformers, silently transforming barren ground into fertile footholds for life. What makes them extraordinary isn't just their ability to survive extreme dehydration and scorching heat, it's their talent for engineering their own habitat. Cyanobacteria, the pioneers of these crusts, secrete sticky filaments that bind loose sand into stable mats, while their photosynthetic machinery pulls nitrogen straight from the air, converting it into fertilizer for other organisms. On Mars, where dust storms rage unchecked and regolith lacks organic cohesion, these humble organisms could be the missing architects for a stable, life-friendly surface. The genius of biological crusts lies in their simplicity. Unlike high-tech solutions requiring energy or maintenance, once established, they're self-sustaining. In places like Utah's Canyonlands or Namibia's Namib Desert, these crusts reduce erosion by up to 90%, anchoring soil against wind and water. Transplanting this strategy to Mars could tame the planet's infamous dust devils not by brute force, but by biological finesse. Picture engineered cyanobacteria, tailored for Martian cold and radiation, sprayed across targeted regions. As they multiply, their filament networks would knit loose regolith into cohesive mats, reducing airborne dust that clogs machinery and obscures sunlight. Over time, these living carpets could expand, creating stable foundations for future vegetation or even human infrastructure. But the real magic happens underground. Cyanobacteria don't just glue soil together, they remodel its chemistry. By fixing atmospheric nitrogen into ammonia, they essentially produce natural fertilizer, enriching sterile ground with the building blocks of proteins and DNA. On Earth, this process laid the groundwork for complex ecosystems. On Mars, it could jumpstart soil development without importing tons of synthetic nutrients. Scientists are already testing extremophile strains in Mars simulation chambers, exposing them to low-pressure, freezing temps and perchlorate-laced regolith. The results: some strains not only survive but continue nitrogen fixation under conditions that would kill most plants. The implications go beyond mere soil prep. Biological crusts are moisture regulators, their porous structures absorbing dew and rare rainfall like microscopic sponges. On Mars, where water exists as frost or buried ice, crusts could help capture and retain fleeting liquid, creating damp microhabitats for other organisms. And because they darken the surface, they might slightly boost heat absorption, nudging local temperatures upward, a small but meaningful step toward thermal stability. What's revolutionary is how this approach flips the script on terraforming. Instead of viewing Mars as a blank slate to be conquered, we'd be collaborating with life's oldest survival strategies, leveraging billion-year-old adaptations to shape a new world. The same organisms that first greened Earth's deserts might one day whisper life into the dust of Mars, proving that sometimes the future belongs not to the loudest technologies, but to the quietest innovators. Terraforming Mars isn't just a scientific challenge, it's a moral crossroads, forcing us to confront what it means to reshape a world that isn't ours. For centuries, humans have altered landscapes without hesitation, from draining wetlands to leveling mountains. But Mars presents a profound difference. It's a blank slate with no voice of its own. If we unleash Earth's ancient minerals and microbes to remake its soil and sky, we're not just engineers, we're playing planetary architects with no guarantee of the consequences. The irony is striking. The very materials that nurtured life on Earth, innocuous clay, humble bacteria, volcanic rock, could become instruments of unintended upheaval on another world. Consider the possibility, however slim, that Mars harbors its own microbial life. These organisms, if they exist, would be survivors of an unimaginable grind, clinging to existence in brine pockets or deep underground, adapted to conditions we barely understand. Introducing Earth's extremophiles could trigger a silent war at the microscopic level, outcompeting or even erasing native life before we've had a chance to study it. It's the ultimate ethical dilemma. Does humanity's survival instinct justify what might amount to interstellar biocontamination? Astrobiologists wrestle with this daily, weighing the precautionary principle, do no harm, against the urgent need to secure humanity's future. Yet hesitation carries its own risks. Waiting for absolute certainty about Martian life could mean stalling progress indefinitely. Mars isn't a museum. Its environment is degrading, its ice sublimating, its scant atmosphere bleeding into space. Some argue that ethical stewardship isn't just about preservation, it's about active restoration. If Mars once had rivers and seas, might we be morally obligated to revive them? The debate echoes terrestrial conservation. Do we fence off wilderness or actively rebuild damaged ecosystems? The difference, of course, is scale. Earth's mistakes can be remedied, Mars's might be irreversible. The heart of the issue lies in perspective. Indigenous cultures have long viewed landscapes as sacred, imbued with rights beyond utility. Modern environmental ethics grapple with similar ideas. Should planets have legal standing? Could Mars someday be granted protections under interstellar law, much like Antarctica's internationally shielded status? These questions aren't abstract. Space treaties already forbid harmful contamination, but definitions blur when survival is at stake. What's clear is that terraforming demands humility alongside ambition. Ancient Earth materials offer tools, not shortcuts. Every mineral we scatter, every microbe we deploy, should be chosen with the care of a surgeon, precise, deliberate, reversible where possible. The goal isn't conquest but partnership, learning to work with Mars's geology rather than overwriting it. After all, the greatest terraforming lesson Earth teaches isn't technical, it's that life flourishes when it adapts, not when it dominates. As we stand on the brink of becoming a multi-planet species, that wisdom may be the most vital material we bring. Right now, robotic geologists are combing the Martian surface with a singular mission: to uncover the mineral signatures that could rewrite the planet's future. NASA Perseverance rover, armed with its pixel spectrometer, scans rocks in Jezero crater for carbonates and clays, remnants of an ancient lakebed where water once pooled. Over in Oxyoplanum, ESA's upcoming ExoMars Rosalind Franklin rover will drill deeper than ever before, hunting sulfates and hydrated minerals that could reveal how Mars lost its water and how we might bring it back. These aren't just academic exercises, they're the first steps in a grand experiment to test whether Earth's oldest geological tricks can work on another world. But the real breakthrough lies beyond reconnaissance. Picture lunar bases doubling as extraterrestrial test kitchens, where astronauts mix simulated Martian soil with bioengineered microbes or crushed olivine to observe reactions in low gravity. The Moon's harsh environment, its radiation, vacuum, and temperature swings, makes it the perfect proving ground for technologies too risky to trial on Earth. A greenhouse dome in Shackleton Crater could pioneer mineral-enhanced hydroponics, while a sealed lava tube might host racks of basalt columns absorbing synthetic CO2. These aren't science fiction scenarios. NASA Artemis program and ESA's Moon Village concept already outline such hybrid habitats, where lunar outposts serve as dress rehearsals for Mars. The genius of this phased approach, it turns uncertainty into strategy. Before unleashing Earth's ancient tools on Mars at scale, we'd refine them in controlled off-world labs. Take lichens, for example, those crusty partnerships of fungi and algae that weather rocks into soil on Earth. In 2022, scientists strapped lichen samples to the International Space Station's exterior, where they survived 18 months of vacuum and cosmic rays. Next stop, lunar greenhouses to see if they can crack open simulated Martian regolith, followed by eventual deployment to Mars's surface. Every step narrows the gap between theory and reality, ensuring that when we commit to terraforming, we're not guessing, we're applying hard-won data. What's often overlooked is the parallel work happening in Earth's own extreme environments. In Iceland's basalt fields, researchers inject CO2 into volcanic rock, monitoring how quickly it mineralizes, a real-time preview of Mars's carbon sequestration potential. Chile's Atacama Desert, Mars's closest terrestrial twin, hosts test plots where cyanobacteria struggle against perchlorate-laced soil, teaching us which genetic tweaks might help them prevail on Mars. These analogues are more than stand-ins, they're sandboxes for failure, where mistakes inform progress without dooming a planet. The roadmap is clear, from robotic scouts identifying mineral deposits, to lunar labs stress-testing ancient material applications, to Martian pilot projects that start small. Perhaps a hectare of engineered soil or a single wind-scoured basin treated with carbon capture minerals. This incrementalism isn't lack of ambition, it's respect for complexity. Terraforming won't hinge on a single eureka moment, but on countless quiet breakthroughs, each one proving that the materials under our feet hold the power to reshape worlds. And with every mission, from Perseverance's tire tracks to moon base prototypes, we're not just exploring space, we're learning how to collaborate with it. From Earth's primordial past to Mars's promising future, ancient materials offer more than just a scientific shortcut. They represent a profound shift in how we approach planetary transformation. For decades, the dream of terraforming Mars has been dominated by grandiose visions, massive orbital mirrors, atmospheric factories, and other feats of engineering that demand staggering resources. But what if the most elegant solutions have been hiding in plain sight all along, etched into the very rocks beneath our feet? Earth's geological record is a masterclass in patience and precision, showing how tiny microbes, mineral reactions, and slow chemical weathering sculpted a lifeless world into a living one. The lesson here isn't just about efficiency, it's about working with nature's rhythms rather than against them. Take basalt, for example. On Earth, this unassuming volcanic rock quietly absorbs carbon dioxide over millennia, locking it away in solid form. On Mars, where basalt carpets vast plains, we could accelerate this natural process, turning the planet's own geology into a carbon capture machine. Or consider clay minerals, which ancient Earth used to trap water and nutrients, creating stable environments for life to take root. On Mars, engineered clays could do the same, transforming barren regolith into fertile soil without a single shipment from Earth. These aren't futuristic fantasies, they're adaptations of processes that have already proven their worth over billions of years. The real breakthrough isn't technological, it's philosophical. By studying how Earth transformed itself, we're learning that terraforming doesn't have to mean domination. It can be a collaboration, a dialogue between human ingenuity and planetary evolution. The microbes that oxygenated our atmosphere, the minerals that stabilized our climate, the sediments that preserved water, these aren't just tools. They're partners in a cosmic project far bigger than ourselves. As we stand on the brink of becoming an interplanetary species, the choice before us is clear. Will we charge forward with brute force, or will we listen to the wisdom encoded in Earth's oldest materials? The answer could determine whether Mars becomes a second home or just another failed experiment. One thing is certain, the universe has already written the playbook for turning barren worlds into living ones. Our job isn't to rewrite it, just to learn how to read it. The future of Mars might not lie in our labs, but in the very ground we walk on. And that's a humbling, thrilling thought. So tell us, which ancient Earth material do you think holds the most promise for Mars? The conversation starts now.